Last time we talked about quantum teleportation. It was one of the basic applications of quantum computing which seemed magical. The idea was to transfer a quantum bit whose state was unknown. You want to transfer it using classical communication and entanglement. Assume Alice has a state psi which can be given to her. She has no idea what the state is going to be, and Alice and Bob are sharing a pair of entangled bits. Now there will be some circuit, some protocol performed which might have classical communication also, and in the end Bob, remember this was Bob, this was Alice, this was also Alice, and finally the state should come to Bob's part. This was the task of quantum teleportation, and it seemed similar to swapping bits on classical computer. This was our target. We also saw a circuit of swapping bits on classical computer without using temporary registers. This was not difficult. And if there were two states x and y, then we get this is on a quantum computer. This was inspired by the way we will swap bits on a classical computer. Given this circuit, question is how to do quantum teleportation. We want to simulate this using entanglement and classical communication. We want to convert this into this. The important thing is we can't apply gates, common gates between Alice and Bob's parts. In other words, there is no way to apply C naughts between Alice and Bob's part. How to do it? You will have to remember that this is the circuit of interest. This is what we want to accomplish. Without loss of generality, we can assume that Bob starts with a 0 qubit. Then we want to simulate this part. I have just reversed the order of C naughts. That doesn't change anything. By symmetry, this should swap between the two states. This is the circuit we want to simulate. Notice that the first qubit or the second qubit in this case is 0. So the control is going to give 0. Hence, this gate is useless. It will not do any changes to our circuit. I can just remove it. If the control qubit is 0, then the NOT gate is not applied. So I can as well remove it because the state is fixed to 0. Once I know this, then the circuit which I want to make looks like this. It would look like 0 and x. This is the circuit we want to simulate. How to do it? There are many features which can be used, but the first thing is that we will do this transfer initially using an intermediate qubit. This C naught will convert into 4 C naughts using intermediate qubits. The reason being, we don't want C naughts between Alice and Bob, the primary qubits. So we will use one more qubit. We will keep it with Alice. This is Alice's intermediate qubit. And then this is Bob's qubit. So this C naught will be replaced by 4 C naughts. And then I will transfer this. So first C naught I have converted into 4 C naughts. Now there is no operation on Alice's qubit using Bob's qubit. The first gate has been removed. How will we take care of others? That's another thing. But remember that we don't care about the state, final state of first and second qubit. And the way it is working, I can introduce Hadamard in the end. Why am I introducing Hadamard? That will be clear very soon, but it doesn't affect to use Hadamard. You can have any intermediate qubit, still this 4 C naughts will transfer, will be equivalent to 1 C naught of the top gate. So I can start with any intermediate qubit. So I will start with 0 and then applying Hadamard to it. And then a very nice property shows that I can move Hadamard on the other side by converting NOT into a Z gate. These two circuits are equivalent. You can take it as an exercise to prove that. This will allow us to move our Hadamards here. What is the circuit? We will have again 3. This is the state we wanted to transfer. This is the intermediate. This is Bob's qubit, which started in 0. Now the first C naught gets converted into Z gate and then Hadamard. Then there is a XOR C naught, the final C naught for the between the intermediate qubit and Bob's qubit, and then there was another C naught which was getting applied to psi. Let me show you. I'm talking about this part. Again, I will switch using H. So I can write H here. This becomes Z. This is just using the equivalent that I can move Hadamard across C naught gate by converting XOR into Z, converting CX gate into CZ gate. This is what I have done. And the great thing about control Z gate is that control and target can be interchanged. That is true. Let's do it. Notice that once I change the control and target here, the control will have 0, so I can remove the Z gate. The first control Z gets removed after switching the control and the target qubit. That was the reason why we switched. Z gate, I have again removed the control, and then there is a Hadamard gate here. Great. It seems that we are in better shape now. If you look at the part of Alice and you look at the part of Bob, there are lesser gates now. The question is how to take care of them. There are actually, in this case, this gate here, this gate here, and this gate here. There are three gates which are getting applied between Alice and Bob, and we have to take care of them. We will notice that these two are simply controlled using Alice. Gate 2 and 3 are only controlled by Alice. No action is happening on Alice's qubit. Instead of using a control, we can measure first and then send the classical bits. That will turn out to be equivalent. So I can transform these two gates simply by measuring the two qubits of Alice and sending that data to Bob. That gives rise to this circuit. H positive, we are almost done. Hadamard, and then there is measurement. This is denoted by measurement, and these two are classically communicated to Bob. And then depending on that, Bob can, on these two bits, he can decide to apply an X or a Z gate. But this will depend on what has been communicated. Great. We have only one gate left as a problem. Notice that this gate is between Alice's qubits. She can apply it because both the qubits are with Alice. Alice 1, Alice 2, and Bob. Only problem is this C0. What should I do with this C0? But if you realize that this part of the circuit does not depend on the state which I wanted to transfer. Alice and Bob started with 0. Alice applied Hadamard and then applied C0. Here, this was the bottom part of the circuit in the first half, and this circuit does not depend on psi. In other words, we can do it a priori before even receiving information about psi. This is another major thing to notice, and if you see this, then you will notice that the final state is 0, 0 plus 1, 1 by root. So instead of applying this later, we can start with the qubits in the state 0, 0 plus 1, 1 by root 2. That means we will not have to apply these states in action. So our final circuit will become, you are starting with 0, 0 plus 1, 1 by root 2. The 0, 0 plus 1, 1 by root 2 will take care of the first Hadamard and C0 gate. You have Alice's first qubit. Now if I look at the circuit, the first half is taken care of, then it only means apply a C0, apply a Hadamard, then measure. Send this classically to Bob, and then Bob's decide to apply X or Z depending upon what is the information received from Alice. And finally, this state should transform into psi. This will give you the quantum teleportation protocol. I can roughly describe it. You can see the exact protocol in the notes. Roughly, Alice will have two qubits. One will be in psi, second will be shared with Bob. It will be entangled with Bob, which will be in the state 0, 0 plus 1, 1 by root 2. This is the first step. This is how they will start. You can say that they have entanglement from before. That's the 0th step of the protocol. In the first step, Alice will get state psi. Then she will apply C0 on second qubit using first S control. Then Hadamard on first qubit and measure both. This information will be classically given to Bob. These are two bits, one from the measurement of the first qubit, one from the measurement of the second qubit. Classically send these two bits to Bob. And then Bob decides to apply X or Z on this information. In the notes, you can see by these states, you can do the calculations and you can verify that the final state of Bob would be psi. I could have directly given you the protocol and showed you the calculations. It would seem magical that finally Bob has this state. But this sequence of steps shows you exactly how you can arrive at the quantum teleportation circuit. The idea was to simulate the swap circuit. And then different C0s were either gotten rid of or were done using entanglement. This allows us to do quantum teleportation. In the video, I have given you the intuition for the quantum teleportation protocol, but make sure that you look at the exact protocol and verify that this protocol